Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is fuses and circuit breakers. Our objective today is to review two common circuit protection devices, fuses and circuit breakers. We'll discuss their intended purpose, means of operation, differences between them, and common ratings. This lecture is largely a review of the material discussed in the Circuit Protection Devices lecture from way back in the Basic Electronics 1 DC Circuit Analysis playlist. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. This lecture's intention is to zero in on two of these devices, fuses and circuit breakers, and discuss the application of these devices to electrically controlled systems. Circuit protection devices are components that safeguard people and property from electrical and fire hazards. You are a circuit protection device. The simple act of just not doing stupid things is the first and most important line of defense when it comes to circuit protection. It is my intention that you understand, appreciate, and respect electricity, not fear it. It is as dangerous as it is useful, and there are laws, natural and man-made, that govern its wise use. Follow the rules. Follow the code. The National Electrical Code is there to safeguard people and property from electrical and fire hazards. Pay attention and don't operate devices outside their intended range, nor excessively overload them for sustained periods of time. If this advice is to be boiled down to a single standing order, let it be this: watch the current. Given our understanding of the basic DC power equation, we realize that power dissipated by a device is proportional to the square of the current through it. It is therefore understandable that it is of primary importance to maintain current at or below a certain predetermined level, since any increase in current constitutes a geometric increase in power dissipation. This is where not only a conceptual understanding of electrical theory comes into play, but also proper instrumentation use and the interpretation of numerical results. It is incumbent upon any individual using any expensive electrical apparatus they wish to keep in working order to continually monitor current. Avoid high current for sustained lengths of time. Pay attention and be prepared to shut it down at any moment you observe unusually high current for a sustained period of time, smell or see smoke, or worse yet, see flames shooting from the system you're working on. Know where the off button is and make sure you got access to it. Industrial systems often have strategically placed emergency stop buttons that allow an individual observing an unsafe action or scenario to immediately disable the system. Familiarize yourself with the location of these switches and know their intended purpose. Modern systems, however, cannot rely on near constant human intervention. It is for this reason automatic circuit protection devices are employed. Additionally, I don't mean to discount preparedness, but I do need to temper your expectations because things do go wrong to even well-prepared people. Understanding basic electronics theory does not grant you invincibility. No amount of conceptual preparation can prevent a faulted component from igniting the moment the power is turned on. The job of circuit protection devices is to prevent such problems from becoming injuries or damaging equipment. Today, we'll review fuses and circuit breakers, both different types of circuit protection devices that basically do the same thing. They open up and stop current flow just like an emergency off switch. They use different means of detection and operation, but ultimately they perform the same function. They stop current flow. Current protection devices are placed in series with the electrical load they are intended to protect, because elements in series with one another carry the same current. This is the most basic of series properties. Protection devices make use of this fact to selectively enable or disable current flow. If a protection device is closed, it allows current flow to the load, whereas an open protection device does not. Fuses. A fuse is a metal alloy element that is purposely designed to melt at a specific temperature and open the circuit. Here are two common schematic symbols for a fuse. Fuses are two-terminal devices placed in series or in line with the load it is intended to protect. For electrically controlled systems, you might find a bank of 3 fuses in the primary schematic protecting a motor, or one or more fuses in the pilot schematic protecting the control transformer. In the event of a short circuit in the primary or pilot schematic, the fuses would melt open and protect those devices in series with it. A fuse has a body inside which the metal alloy element is soldered or welded to the contacts, end caps called ferrules, or sometimes blades. Sometimes the body is glass or transparent plastic, and you can see the metal alloy element. Sometimes the body is opaque and filled with a quartz sand filler, for reasons I'll return to in a moment. When the fuse is intact, the path between its terminals is a closed 0-ohm path, and the circuit operates as intended. When opposition decreases and current reaches or exceeds a certain predetermined value for a certain amount of time, the fuse melts and the path between the two terminals opens and stops current flow by becoming an infinite resistance. The fuse is essentially acting just like a switch in series with the electrical device it is intended to protect. If the switch is closed, current will flow. If the switch is open, current will not flow. Fuses differ from traditional switches, though, in that fuses are one-time use only. When a fuse blows, it is rendered inoperable, and here's the important part. Once the fault that caused the blown fuse has been identified and rectified, the damaged fuse must be replaced with a functional fuse with the correct rating. Fuses have 5 common properties: rated current, time delay, rated voltage, breaking or interrupting capacity, and rejection type. We'll briefly discuss each property. Rated current. As mentioned previously, the business end of a fuse is a metal alloy strip that quite literally melts when current in excess of its rating travels through it. When you need to protect your circuit against a draw in excess of 5 amps, you specify a fuse with a current rating of 5 amps. Follow NEC guidelines for determining the recommended fuse size. Time delay. Depending upon the composition of the metal alloy element, this opening action could happen quickly in the case of a fast blow fuse, or take a measurable amount of time to do so for a slow blow fuse. Recall that motors can exhibit a phenomenon called inrush current, in which an intense but brief draw of current occurs when the motor is first started. Inrush current can sometimes be in excess of 6 times regular operating current. A slow blow fuse is often used in series with a motor supply voltage by allowing the temporary passage of such high current, but sensing sustained current draw, the fuse blows after a predetermined time. The delayed action of a slow blow fuse is a heat transfer relationship between current and time. The higher the current, the faster the fuse will blow. The lower the current, the slower the fuse will blow. Ideally, the inrush current for a motor and a properly sized time delay fuse will be quick enough to prevent the time delay fuse from blowing. Correct fuse sizing prevents unnecessary disruption under normal operating circumstances. Rated voltage. In addition to rated current, a fuse has a rated voltage, which indicates the maximum safe operational voltage limit. Larger voltages require physically larger fuses to interrupt the same amount of current, because even air could become a conductor with a dangerous arc forming between 2 high voltage points in close proximity. Breaking or interrupting capacity. Fuses also have what is known as a breaking or interrupting capacity, which is the maximum current that can be safely interrupted by the fuse. The breaking capacity should be higher than what the power supply is capable of producing during the event of a short circuit. Finally, some fuses are designated as rejection type fuses, in that physical modification of one of the 2 terminals comprising the fuse makes it impossible to insert a fuse with a different rating in the same fuse holder or similarly a fuse block. This is accomplished with an annular indent on the ferrule of some fuses or a slot cut into the blade of others. The dimensions of the annular indent or slot do not allow an improperly rated fuse to be inserted into the same fuse holder or block. Here's a non-rejection type fuse being employed in a fuse block. Note the flat and featureless ferrules. Here is another fuse block designed to hold a rejection type fuse. Quick note about fuse holders. Do not open them while the system is operational. They're not intended to be on and off switches. Recall that even air can be considered a conductor between 2 high voltage points in close proximity. A purposely designed means of disconnection accounts for this possibility by providing a means of quickly extinguishing any arc that may form between the 2 points. As we'll learn later, circuit breakers designed for this purpose employ some pretty exotic means of doing so. Once the system is properly shut down and properly locked and tagged out, only then can the fuse holder be opened and the fuses inspected and/or replaced. In addition to following proper lockout and tagout procedures by keeping the fuses with you while you perform a maintenance procedure establishes yet another layer of protection, preventing the inadvertent startup of equipment.